Hi everyone. In this video, I'm going to talk a little bit about conserved currents. Now, previously, you thought about conservation principles in previous physics classes where you had maybe some energy, and energy is conserved. And when we talk about energy, maybe you think about, oh, I have some energy in this region of space, and maybe the amount of energy associated with this region of space changes as a function of time. And in non-relativistic theories, you can think about energy and a certain amount of energy in a region changing as a function of time. And that's a very fine thing to do. And you can think about energy flowing in or out of that area. And that's okay. But thinking about it that way really makes time, again, this special thing. We've parameterized maybe how much energy we have. We've written it as a function of time. We instead, in relativistic theories, always want to be thinking in terms of space-time. And so it's going to be a lot more natural to think about currents rather than just thinking about, for instance, the energy in this region as a function of time. And you've studied currents before. And so, for example, we talk about the electric charge. And electric charge is a conserved thing. And maybe previously you would have written Q as the total charge, maybe in some region, which again, in general, maybe charge is flowing in and out of this region. So Q would be some function of time. It'll be slightly more natural to think in terms of charge density. And then we can think about a current density, which is thinking about our flow of charge, or our flow of charge density, if you like. And what we can do is we can combine all of this information into a 4-vector, which is now starting to look like something that's more relativistic, where the time component of our 4-vector is going to be our charge density, and then the 3-vector of our current density are the spatial components. And this object is a much more natural object in relativity. Again, there's nothing wrong with the other ones, but they aren't, it's harder for those to see if those are explicitly obeying the symmetries of relativity. Whereas if instead we combine them into this 4-vector, 4 vectors, again, are these nice objects that we understand in relativistic theories. And so that's what we're going to do. And I've explained this in the example of electric charge, but we can have these current vectors for any 4 vectors for any conserved quantity, not just for electric charge. So again, so maybe I should box this. This is not just for this example. This current 4-vector is a thing that we're going to think about for other things. And we will say that it is conserved. So this 4-vector is conserved if this equation holds. And we can better understand this if we expand our derivative. And remember, we actually write out this dot product. Which we can write in a sort of simpler way. So this is d rho dt. So that is, how is our charge density changing with time, plus del dot j, which is just, a simplified way of writing this object up here. So what does this thing mean? Well, it'll become a little more evident if we integrate both sides of this equation, right? What are we doing here again? I've declared that this thing that I'm boxing above tells us that J should be thought of as a conserved current. And I want to better understand that. And so we're going to manipulate this equation a little bit. So if we integrate both sides, then, okay, 0 integrated is still just 0. And I've just separated my terms into two separate integrals. Now, the left hand, or this first term on the right-hand side, we can just reverse the order of doing, here it looks like we're doing taking the derivative, then integrating. Instead, we're going to pull that derivative out and do the integral first, because then you notice that this thing is just the total charge Q. So this is dq dt. Now, with this other term, we can use the divergence theorem that hopefully you've seen before in your multivariable calculus class or your mathematical physics class, or hopefully both. It's something that you should review if you aren't remembering it. So look up the divergence theorem, which tells us this second term can be rewritten instead of as a volume integral as an area integral of j dot dA, where we're integrating, this is some area enclosing a volume. And what volume is that? It was the volume that we were integrating over. So again, here we were integrating over some volume up above. And this term was the change in charge in that volume. And to make this really explicitly clear, we can move this dq, this is all equal to 0, right? We can move the dq dt to the other side and say dq dt is equal to negative this integral. So again, this is telling us that the change in total charge in a volume, a given volume, just again, it's just some region, you choose what that volume is that you're considering, is equal to, this is telling us the current flowing out of the volume. And it's out, that's why we have this negative sign. So this is telling us that it's a conserved charge. And again, here I'm using Q, which might feel like electric charge, and that's a nice analogy to keep in mind. But this could be any conserved quantity, right? It can be energy, it can be momentum. It's the change in that conserved quantity in some region is equal to the amount of that charge flowing out of that region, right? The change in the charge inside the region is related to how much charge is flowing out. And again, this thing, which maybe is easier to understand from previous physics classes, what I've just showed is that's equivalent to this thing that I'll now even put in a red box because it's so important. This is how we're going to write that same thing in this class. So we're going to deal, instead of just with thinking about conserved charges, we're going to think about these current 4 vectors. And the statement about that 4 vector being conserved is the statement that d mu, j mu, if j mu is our conserved current, that derivative vanishes. Okay, so that's a little bit on how we're going to think about conserved charges and how really instead it's going to be more natural to think about conserved currents in relativistic theories.